Welcome to The Explainer. Okay, I am absolutely pumped to dive into this with you today because we're tackling the actual holy grail of video game graphics. We're talking about photorealism. For decades now, developers and engineers have been chasing this dream, right? The dream of rendering virtual worlds that are completely indistinguishable from our own reality. And the secret sauce to making that happen? Well, it basically all comes down to the crazy complex math of how light behaves. So let's jump right in. To really understand where we're going, we have to recognize just how aggressively the gaming industry is pushing for fully dynamic, ray-traced futures. As highlighted by rendering engineers like Oles Shishkovtsov and his team during their groundbreaking work on games like Metro Exodus. The future of rendering relies entirely on hardware ray tracing. We are officially moving away from smoke, mirrors, and baked-in illusions. We're stepping into an era where we actually simulate the true physical properties of light. And we're doing it in real time. And that brings us directly to the core concept of our explainer today, global illumination, or GI. If you've ever played a game and wondered what makes a flat, lifeless 3D scene suddenly look breathtakingly real, this is it. Global illumination is the computational process of simulating how light doesn't just hit a surface and stop. It bounces. It picks up color. It creates those beautiful soft shadows and ambient light in the dark corners of a room. It's absolutely essential for realism, but historically, it carries a massive, massive computational cost. I mean, simulating millions of light bounces in a fraction of a second is incredibly demanding on hardware. Now, what's really interesting here is what lighting actually looks like under the hood. A virtual space is basically filled with this massive grid of floating spheres, known as probes. These probes represent a discretized 5D light field. Basically, that means they capture light intensity and direction from all angles in 3D space. They just sit there in the environment, totally invisible to the player, gathering data on the geometry and the light bouncing around them. Then they pass that indirect lighting information onto the actual objects you see on your screen. But naturally, this creates an unbelievable challenge for software engineers. The big question is, how on earth do we light a sprawling, dynamic virtual world using millions of these data-gathering probes without literally melting our graphics cards? We all want maximum visual fidelity for sure, but we only have a very strictly limited amount of computing power per frame. To answer that, here is our quick roadmap for today. 1. The quest for photorealism. 2. The global illumination bottleneck. 3. Working smarter, not harder. 4. The guiding function. 5. Seeing the results. And 6. The future of rendering. Okay, kicking things off with part 1, the quest for photorealism, seeking the Holy Grail. Moving right along to part 2, the global illumination bottleneck, uniform grid flaws. So the current standard that actually creates this huge bottleneck is an algorithm called Dynamic Diffuse Global Illumination, or DDGI. Now, don't get me wrong, it's a fantastic technique, but it has a very rigid uniform process. First, it places a uniform grid of probes across the entire environment. Second, it generates and evenly distributes tracing rays outwards from every single probe in a stochastic spiral pattern. Third, it takes all that irradiance and visibility data and updates a 2D atlas. And finally, it interpolates that data to actually shade the pixels you see. But here is the critical flaw in vanilla DDGI: uniformity. Updating every single probe equally, even the ones just sitting in perfectly dark, static, unchanging corners of a map, is a massive waste of processing resources. Just imagine spending precious computing power checking the lighting inside a sealed, totally empty closet 60 times a second, while at the exact same time failing to update the lighting fast enough on a rapidly opening door right in front of the player's face. It's super inefficient, and it quickly bottlenecks the system as probe counts increase. Which brings us perfectly to part 3, working smarter, not harder, introducing AGI. Let's contrast these two methods because it's a real game changer. DDGI uses uniform resource allocation. Think of it like a team of security guards uniformly patrolling an entire empty building on a super rigid schedule. You're going to run out of guards very quickly, right? ADGI, on the other hand, stands for Adaptive Dynamic Global Illumination, and it uses non-uniform allocation. It works way more like motion-activated security cameras. It completely decouples the compute resources from the total number of probes, meaning it focuses solely on where the light or geometry is actually actively changing. So how does this scout and focus adaptive strategy actually work in practice? Well, every single frame, AGGI traces a very small number of pilot rays, basically little scouts, to scan the environment for changes. It then uses a specialized guiding function to highlight the critical areas where the lighting is, actually doing something. Finally, it employs what's called Markov chain metropolis sampling. That's essentially a highly advanced predictive algorithm that dynamically targets all of your heavy computational resources precisely at those changing areas. Let's dig into that math just a bit in part 4, the guiding function, the math behind the magic. To figure out exactly where to send that compute power, the algorithm first has to build a map. It constructs this guiding function by multiplying our heuristics, which is just the current state of the environment, like whether a surface is close to the camera or undergoing some temporal change, by the sample feedback, which is the stored irradiance in the probes. The result is basically the algorithm creating a highlighted priority zone. It's the math literally shouting, "Hey, the lighting is changing right here. Look at this." And this brilliantly illustrates metropolis sampling in action. Once that priority zone is identified, the algorithm tightly clusters the computational ray samples right inside that highlighted region. Instead of spreading our rays uniformly and thinly across the whole environment, this Markov chain algorithm acts like the cavalry rushing in. It dynamically allocates our processing power to evaluate only the absolutely critical active areas of the virtual world. And the ultimate payoff of all this math is amazing. Because we aimed our computational samples squarely at the active zones, we're able to reconstruct the lighting function with heavily reduced errors exactly where it matters most. It is a hyper-focused approach that rebuilds the lighting information perfectly for the player's eyes, while comfortably and safely ignoring the static, boring areas that just don't need updates. Time for part 5, seeing the results, proof in the pixels. When you compare the actual pixels, the difference is night and day. Imagine a dynamic stimulus, like a heavy gate suddenly opening inside a dark tunnel. The older, uniform method simply cannot update its probes fast enough, because, remember, it's busy wasting time checking the rest of the map. As a result, the tunnel remains artificially dark, a massive, noticeable visual lag. But AGGI? By sending all its resources straight to that opening gate, it reacts instantly, calculating the new indirect light pouring into the tunnel absolutely perfectly. Tracking this frame by frame over time, you can really see how the rendering engine behaves. AGGI robustly handles transient changes, so whether it's sudden flashes of light, explosions, or rapidly moving geometry, it does it all without stalling the overall rendering engine. It captures the light exactly when and exactly where it happens. No lag, just pure realism. And the raw performance gain? It's staggering. AGGI offers an incredible 1.7 times higher performance compared to an optimized version of the older method. That's a massive leap in rendering efficiency for any developer. To put that 1.7 number into perspective, let's talk milliseconds. In a real-time game running at 60 frames per second, you only have about 16.6 milliseconds to render an entire frame. The older uniform method takes 26.8 milliseconds to calculate the lighting alone. It completely bottlenecks the entire system. AGGI drops that render time down to just 15.6 milliseconds, literally saving the frame rate. And get this, it does it while actively handling a scene saturated with over 2.3 million light probes. Just incredible. Finally, let's wrap up with part 6, the future of rendering, limitless worlds. The absolutely crucial takeaway from this whole explainer is this. By decoupling the performance cost from the sheer number of probes, developers are completely freed from previous limitations. Because our adaptive sampling operates independently of the total probe count, developers can now scale a level to feature millions of probes natively. The environment can be infinitely larger, infinitely denser, and infinitely more detailed without grinding your graphics card to a halt. It's a breakthrough that completely changes the paradigm of game design. Which really leaves us with one final thrilling question. If dynamic, real-time lighting calculations no longer bottleneck our hardware, What actually limits the size and complexity of our virtual worlds next? It's a wild thought to take with you. Thank you so much for exploring this incredible leap in rendering technology with me today.